Thank you very much. You guys can hear me well?
Yeah.
Awesome. So I know this is a session after lunch, so we'll try to make it entertaining, mind expanding. I can take some questions in the middle. I have a bunch of stuff to go through, so maybe I'll kind of pause at some points to take more questions. Let's see how this goes. So making this as a reel of knowledge graphs, let's also talk about GraphRAG. Who heard about GraphRAG? A lot of people. Awesome. So about myself, I wear many hats. You can see me in a hat, also around the halls. I'm an AI community architect at NumFOCUS, which is a graph database company. Who heard about NumFOCUS? A bunch of people, awesome. I'm also a co-founder and convener of multiple organizations. That is kind of a unique career path I cut for myself. So I co-founded the AI Alliance and also Open Source Science Initiative when I was at IBM. And Open Source Science is a top-level initiative at NumFOCUS. You can see our table with both of these banners outside. Also, I'm a founding chair of Generative AI Commons at the Linux Foundation, right? And so I kind of live in the overlap of open source AI and people, right? And effectively, a lot of this stuff is driven by people. We're all here for a reason, right? We could have stayed at home and read a bunch of blogs, but we chose to come here because I think, especially in the time of uncertainty, a lot of best practices established by a convening group of folks like here, right, like us, and deciding collectively what we're going to do. So I'm founder of organizer of Bay Area AI, which is the biggest, deepest, oldest, longest running AI meetup in the world. We run basically since 2015 as an NLP meetup, and through all the stages of grief or happiness of AI, NLP, machine learning, data mining, data science, deep learning, finally AI, right? Everything is now AI, but we went through all of this. In each generation, I think we hosted state-of-the-art talks. And in my other life, I'm a photographer. I have a lot of photos in the cloud. You can see me wearing my camera everywhere, and my ratio of kids to cats to dog is 4 to 2 to 1, all by the numbers. So GenAI is fashionable, right? Like you've seen GenAI, and people flock to GenAI. I'm actually pretty impressed. Like not everybody is at this talk. LLM, and like in this conference, actually, it's kind of very balanced, right? But generally, you have a conference with LLM talks. It's completely oversubscribed, and everything else is empty. And this is, by the way, an actual handbag in the shape of H100. You can buy it for $1,000, which is much cheaper than an actual H100. I found it on eBay. And we don't know why things are fashionable, right? We don't know, even if a scientist is very hard to understand. This is a people phenomena, which kind of hints at LLM and GenAI is also a people phenomenon. A lot of things we don't know because it's fashionable. However, one thing I want to posit, which we forget about LLMs and GenAI in this context, is that everything which an LLM emits is data. It's not knowledge, right? A source of confusion in a lot of GenAI applications and discussions is that we treat it as if it were sentient, or is it, if it emits knowledge. And this is very different from other computer systems. We understand that they do not produce knowledge. And knowledge, what is knowledge, right? We'll need to come back to this, but just, hold this thought. So this talk is about, knowledge graphs and open source. So this is just an example of what's happening in open source. There is this amazing Twitter/X space called Thirst AI, run by my friend Alexy, who is a developer relations advocate at Weights and Biases. You should listen to it. It's 8:30 a.m. Pacific time. I come from California. 2 hours of packed updates, everything. Open source models, closed source models, benchmarks, leaderboards. And every week we have 2 hours that barely fit. They have breaking news, deployments, happens in real time, right? So this is just an example from September 5th, right? So 3 updates, right? There was somebody fine-tuned Llama with reflection and beat everybody else. Like it was in the middle of leaderboard, right? So it was basically, leaders of general LLM, right? There was OpenAI, there was Google, there was Matt from IT, and then there was, Asia and so forth, right? So, by the way, yeah, this is what's going to happen, right? It's flipping. It's flipping from presentation mode by itself, but it actually comes back. So I'll have to do that. So I'll have to tickle it, right? And then AI Institute released an open source ensemble model, and it released into the true open source fashion, which means weight, code, data, and paper. There are 4 things. If you don't get 4 things with an open source model, it's not open source model. Llama is not open source model. You don't get all of this. You have to be able to reproduce a model completely with infrastructure code and with a paper describing this. And also, because we're in Microsoft, it's a hint, I'll mention one amazing thing which transpired that week. So somebody made the biggest open source deployment in history of software. 1.5 billion machines were updated with a piece of open source software, with an open source package, and nobody knew, and still probably doesn't know why, right? That happened. So does anybody know what it was? Does anybody have any idea? Hint, this is not the CrowdStrike bug, right? Which is comparable size, but not. It was not open source deployment. So I guess, it's a very arcane knowledge. So this is something called RWKV, Rockwood. And so when I was the founding chair of GenAI Commons, one of the projects we inducted into Linux Foundation for AI and Data, LFAI, was this project. So this is an open source transformer alternative architecture, right? And so this is basically, descent of Boltzmann machines. It claims to have lower power consumption, infinite context window, right? It says VRAM. And so Microsoft deployed it, right? It went to all the Windows machines. We don't know why. If anybody is from Microsoft here can enlighten us, I'd really like to find out. I don't think we found why this happened. But I mean, obviously the idea is that it's going to use it in some way, right? And there's a plan probably to use it. Somebody's working on this. So this is just an example of what's going on. Like a lot of things we don't know. But I think it's also indicative of where this is going. So I'm a firm believer in open source AI. We have AI Alliance, which is IBM, Met, and 100 other companies visit the booth outside. Also, Open Source Sciences and NumFOCUS initiative. If you care about science, chat with us about that. So I'll do a very brief introduction to Neo4j. Most folks know this, but we'll emphasize some points, right? So basically, it's a graph database, right? And it's used for storage of graphs, and we use property graphs. So we have labels, we have edges, and we call them relationships. And then we can do graph data science. And basically, Neo4j exists for roughly 20 years. It predates current wave of AI. It's very much used, I think, category defining databases, created the category of graph databases. And graphs are used everywhere, right? A lot of algorithms, from customer behavior and fraud and churn and so forth are actually running with graphs. And so we all know relational model. And when you work with graph database, you suddenly realize that relational databases are very weird because we naturally do not think in terms of tables. Like this is how we represent person assets. So right, we have basically persons, we have assets, and we have effectively a key table, right? And this is not how people think. We really don't think this way, right? We think we traverse these relationships, right? We think in terms of hops, and it's effectively, we think like this. And when I started kind of comparing these two things, I realized that a lot of complexity in our apps come from actually trying to pinhole the data we have into relational tables. So it's just a thought, right? Like it may be much easier. I think the initial kind of origin of relational databases comes from a lot of this is actually academic, right? But and maybe accounting, but a lot of real world data. It's probably better represented as graphs, right? This is much more natural. This is how we think. And now, by the way, there is a query language. So relational tables have SQL. We have now GQL. And GQL is a descendant of Cypher. This is the first query language adopted by us after SQL. So like in 40 years, we finally have a new language finalized in spring this year. And now a lot of vendors can actually implement it. One of the best implementations of GQL is actually by Google. The Spanner database uses GQL, which is pretty fascinating to me. And we can now, I think, see much more development in terms of graph databases, right? So we have effectively property graph. It includes graph data science, and it integrates with a lot of different vendors. For instance, there is a graph data science for Snowflake, right? You can use it with relational databases. And the queries are using pattern matching, right? So this is a nice query language. If you are a programming language geek, you will have fun with Cypher. Now, what does have to do with GenAI GraphRAG? So let's kind of look at GraphRAG. So who heard about RAG? Right, retrieval augmented generation. The reality is that majority of RAG systems, probably 99%, are vector RAGs, right? So they're not also vector RAGs because they do not usually need to distinguish themselves from GraphRAG. And so I make this distinction because we here have the GraphRAG, which in some ways supersedes vector RAG and has features which are different from it. Right, so let's look at kind of where do we get the data, right, for this retrieval. So a lot of this is unstructured data. This is where usually vector RAGs live, right? They say, let's get a bunch of documents, let's get a bunch of company data. Your company data is dark data. It's not on Google, right? It's your valuable data, but it's dark data because it's not searchable easily unless you have some internal search systems, which all usually suck, right? And so like you cannot really get a hold of this. It's Word documents, it's PDFs, it's emails, it's Slack, right? Maybe images. Now we have pure data. Pure data is data somebody carefully curated and forged into the relational schemas, organized in other ways. Usually it's in a database, right? And so you can query basically some standard analytics questions from your pure data. And but what's interesting that majority of the questions arise at the intersection, overlap of this, right? We need to mix text and data. This is where it becomes hard. This is where vector RAGs are making the inroads, because if you want to ask complicated questions, give me all internal Slack discussions or contract drafts related to this transaction, this relationship, right? You need to extract some pure data, and then you need to find unstructured data, or vice versa, right? And so basically, this is where RAG lives, right? This is where it exists. But we believe that the knowledge graph essentially is, most applicable in this case. So knowledge graph is basically a kind of graph where we think of data as knowledge and we put it in there. And so this is, I think, the key distinction. And I think it should inform most of GenAI development that, right, like knowledge has to be validated by humans. You cannot declare, a computer cannot declare that some output of it is knowledge. Knowledge at some point is looked by a human put it in a database, right? A human validated it. It may be an automated process, but you have to have some kind of validation. You have to vouch for an entry in the pure data that it's knowledge. And so GraphRAG effectively is using knowledge graph to do this, retrieval using text and or structured data and pure data, which is in this case stored in knowledge graph. Right, and so we can match patterns in graph using graph languages, and you can use various graph algorithms and retrieval techniques, which we know and love from our CS 101, right? And we can also use vector RAG. So, GraphRAG does not mean you should abandon vector RAG, and kind of I'm arguing for using both, and I want to highlight the features of both. So, as an example of real-world knowledge graph, I can give you the map of open source science. Map of open source science is a project that we started. I founded Open Source Science and MOS, Map of Open Source Science, in 2022. And we made it a NumFOCUS project. And later some folks joined, so Tim Moneman is outside there, he's at IBM. And John Starr is a program manager for Open Source Science at NumFOCUS. John is talking about this in much more detail in this track, right, later. So I really encourage you to attend John's talk and learn more. But basically, what is a knowledge graph, right? It's effectively the graph which highlights internal knowledge structure, right? So the records, basically the nodes, at this point they correspond to relational records. Right now we have sets, right? Because there are multiple kinds of nodes, right? There can be people, there can be open source projects, they can all be represented as nodes, the entities, right? And then they have relationships, right? So in this case, the relationships will be direct edges. In the relational databases, you will have to create, foreign key relationships between them. And then you can have patterns, right? Because you can look at the graph database and you can actually identify various kind of patterns. And then you can overlay layers, right? You can basically subset these graphs. So you can do a lot of these graphs. Specifically in MOS, this is the entities which we have. We have people. These are developers who who focus on specific case. Open source used for science, and fortunately it includes computer science and GenAI as an example, right? And so scientists write papers. In these papers, they now cite open source. There is now a mechanism to cite open source project. There's a journal of open source called JOS. And you can, if you have an open source project and you want to be cited, you can write one-page article submitted to JOS, and then you can have an ID and you will be able to cite it. So I highly recommend everybody, even like if you have any kind of proximity to science, if you like science, if you read papers, write one-pagers about your projects and publish them, and then people will create this graph for you. So then we have organizations, right, who support these people usually deploy, like Microsoft or Google, and also interesting organizations do, they fund these projects. Open source doesn't grow on trees, and so universities receive a lot of grants, for instance, right? And instead of begging university administration to give you money for open source, people at the University of California, Santa Cruz, what they've done, they went to IP transfer office, they counted how many millions of dollars were bought by industry, how many of these projects had been built by open source, right? And then you can come and say, open source made you $2 million, right? Give me more so I can hire more students, so I can develop more open source. So actually, if you attribute open source funding and grants to these projects, you can actually make good cases for development. So this is one of the use cases we have for MOS, and John will talk more about it, right? So in the kind of graph parlance, we have these nodes, right? The nodes can be different kinds. They can be papers, users, right? And as usual, they are basically records, right? So each of them is effectively a little JSON object. And we have relationships, right? So author writes a paper, the author can write code the project, and the paper can cite, and we can tag it. So this is a statement underneath in Cypher, right? Cypher is a little graphical, like cute representation. The nodes are in parentheses, relationships are in brackets, and each of these can be nested, right? So you can hang JSON objects. And of the nodes, you can actually have anything. So normally, if you deal with embeddings, you just put embeddings into the nodes, right? So you can actually have a strict superset of vector array because you can put anything in the node, including a vector or a bunch of vectors, right? And so what does knowledge graph actually give you? It gives you context, effectively what you have, right? You have context because these relationships and tags create a context for an LLM, and it's much richer context than a text window, right, which you drop into a vector database. So this is a URL to a project at NumFOCUS called LLM Graph Builder. So it's hard to build this thing, right? So what we've done, we created an LLM Graph Builder. You can drop a bunch of PDFs. Again, I don't have the time to cover all of it, but if you go there, you could see a beautiful app. It's open source, you can deploy it, you can drop things into it, it will build the graph for you. It will not be perfect, right? You'll have to deal with it, but this is a very good start. When we demo this and people want to buy it, and we say, like, this is just a demo, guys. This is a DevRel demo, right? But you can play with this. It's really, really powerful. And when we go to conferences, we show it in the booth, and it's fantastic. We can take all the attendees of a conference and drop it in there and see you can find relationships. So I'll go a little bit through kind of GraphRAG, right? The example will be SEC Edgar financial forms, and we're here in the financial capital of the world. It's very appropriate, right? It's basically a database where companies and investors have to report, right? Publicly traded companies and investors. So there's a 10K form and there's form 13 about companies and investors, right? And so what the data modeling looks like with GraphRAG, you have to create a minimum viable graph, right? So minimal viable product, you start with a small, simple graph structure, and you kind of bare bones graph, and then you grow things on this graph. And that gives you kind of an idea how you build these graphs, right? And you create, and you enhance, and you connect. So you create the structure, you create the nodes and relationships, you enhance them, and you enrich them with various attributes and data, and then you connect them, right, in terms of their meaning. So it usually all starts with chunking, we're not different. And to me, it's a bunch of voodoo because people basically say, like, let's take a bunch of text and split it into chunks, right? Because it will normalize kind of unit of text, and vector arrays usually go through some kind of art and craft of, like, let's have small chunks, let's have big chunks, let's see what happens, maybe we should mix them, right? But like, we have to do it in some way. It's not as important with the GraphRAG, but we'll chunk it. So we'll chunk it into pieces, and we have a bunch of chunks. At this point, we're no different from vector RAG, right? We have a bunch of nodes. Each chunk becomes a node, right? And we'll basically replace them with embeddings, right? So we have embeddings, and so we can do vector search on them properly. But now we'll start to do something different. Now we'll link them all, right? Now suddenly we have a relationship between all these chunks. So the document is represented by a linked list of chunks, and which is great, right? So we have this very small, graph where there are chunks floating and linked to each other. Now we really start doing something different, right? Basically, at the previous step, here the vector RAG stops, right? You don't even have links between chunks in vector RAG. You don't know where they're going to fall. Because if you're talking about the Apple computer company, chunks about Apple and iPhone can end in one place, Apple without iPhone will be in a different place. You may confuse with fruit, yep?
How do you establish the links between different chunks based on the...
No, the links between chunks is just order of textual, order of document. Yeah, so this is a very primitive, right? There is no magic here. It's a very simple, like we're going to do very simple things which are going to lead to good results, hopefully. Right, so this is an order of chunks. But now what we can do, we can summarize it, right? There is a lot of different algorithms. We can ask LLM to summarize the document, right? So this thing is calling out in LLM, right? Like it's an addition, just like RAG. So we can actually generate a bind, like we generate the embeddings with LLMs. Now we can go generate a summary, and we can prepare the summary, and we can link all the chunks to the summary. So now there is a chunk floating in soup of chunks, and you don't know it's about Apple, the fruit, or Apple, the company. You can always look at the summary, right? And you can make LLM basically categorize it. So now you have actually a much more meaningful representation of the document, and you can do whatever you want of chunks, small or big, and now they're all pointing to a summary, right? And now 4 and 13, so now we have some, like we can basically use it as a minimal viable representation for 10K. Now we have 4 and 13, which is investors, which is a lot of fun, because investors basically, investment funds, they invest, they have managers, they invest in companies, and they live in places. Like there is really rich data here we can play with, right? So we basically put them all in a graph. We have managers, we have companies, and the managers own stocks in companies. We can put it all there, right? And then we can do a really fun thing. We can locate them. We can say where the manager is located and where the company is located. This is reported data. And this is super fun because we can see what if an investor meddles a lot of the company where he lives nearby. This is an interesting observation, right? Are they kind of doing something interesting there, right? Are they investing here in the same way they invest somewhere else? And I'm not going to answer this question, you could just do it, right? And so now what we finally do, right, there's this final beautiful connection where we connect the company to the Form 10K. And now we can ask a bunch of questions here, right? We can ask, is this investor invested in this company which does lithium-ion batteries? If there's a shortage of lithium, which managers can be affected by this, right? And we cannot, try to ask this question from a vector RAG. Right, this is a very hard question to ask of a vector RAG, right? Because all the vector RAG looks with dots in the multidimensional space. All the nodes just squished into a dot, and whether in proximity and neighborhood of this dot will actually relate to, supplies of lithium-ion batteries and the investors, is a question. So what we've done, the structurally here, right? And this is the kind of process we went through. We created, we enhanced, and we connected SEC financial forms. Right, and so this is kind of the steps corresponding with the graph objects and relationships we went through here, right? And so I want to kind of stop here and kind of outline a bit more directions of the AI graph stack, right? So as you've seen, right, we basically, how do we build this graph? I don't have the time for like a full-blown demo here. I will show you a link to the open source project which is doing this. Like all of this will be, it's available actually as a GitHub repository, and the versions of talks about SEC data exists on YouTube. So I'll give you a name on the channel where we publish it, right? But kind of what's really interesting here, right? So we need context, right? We need context to deploy LLMs in production. The context we obtain now with RAG, right? And so vector RAG basically gives you effectively a vector database with TF-IDF search, which existed right for 40 years. And you can now look for neighborhoods of these dots. And then you can do some interesting things. You can change chunk size, and you can kind of control the graph like little graphs, but it's not full-blown graphs. And GraphRAG actually gives you a way to create this rich context, right? You have long range relationships between pieces of data which are very hard to glean from any kind of text window. It doesn't matter. It will be 2 million tokens, right? Like you will have, 1 billion documents. Like no context window, I think, will solve this problem because there are relations which are just not explicit in the text. They're not there. Like they're not going to be solved by masking words in any context window, right? This is more complex structure. I don't think, at least at this point, we can see how this can be easily implemented. But more importantly, right, we need to connect. So the graph which we've seen should be correct. The LLM can make mistakes, but you're basically supposed to go and validate this graph, right? You should do spot checks on this. You should actually make sure that all this data is correct, right? Like if you do proximity search on this geospatial search, if you find like these people on 2 different continents, so the distance is longer than expected, you should look at it. Like you should find anomalies, right? So I think the key difference here, knowledge graph you can actually validate and you can curate it. And some companies already have a knowledge graph. So all 5 Fortune 500 companies are customers of NumFOCUS, and they store amazing things like auto manufacturers store the whole car digital twin on the graph. You can know, an engine contains all these parts, and a cylinder contains a spark. Like all of this will be hierarchically mapped out in the graph, and you can do the various things, right? Like you can get enumerations. Now, what this GraphRAG actually gives you in this context, you can ask exhaustive set of questions. Like when I mentioned this example, give me all the investors affected by the shortage of lithium-ion batteries, to actually give you a complete list of investments in this database, right? Or give me just a very simple question, give me a list of investors in the company. It turns out it's not, unless you have a table, right, which, vector RAG can, well, LLM can actually extract, right? And the table says all investors in the company, right? Like, probably you will not find it because investments are transactions. The transactions will be dropped into this graph. You can edit it in real time, right? When we see an investment, you can drop the triple investor invested X investment company Y. You can drop it in the graph. It will be immediately available for GraphRAG, right? This is not a static snapshot. You can keep adding the edges to the graph and the nodes, right? And so the beauty of this, we have an example, I think, kind of where it really shines, right? You can ask a vector RAG, give me all the investors in the company. And various kind of vector RAG retrievers will give you, some of them will actually be naive and not give you anything because it's hard to find investors in finance in the company. But then it will give you like 3 or 4. And GraphRAG will give you all of them because they were connected at the stage of the building the graph. Like if they're in any transaction which was seen in any document, they will be added to the graph. So what happens in LangChain, there is a retriever with a window which gives you several candidates, right? So what you can do before returning the answer to the user, you can do something with the candidate documents. So what we do in this example, we take the node and we just traverse it, right? And so we understand that your question is give me all attributes of a node. And a graph can give you an exhaustive and closed set of answers, which is complete and correct. Right? And vector can never give you this. It will never give you complete set, right? Because it doesn't know. Also, there is another beautiful question. Give me something which is missing. Give me a node which misses something. Try to ask this question. Like, it's a very hard question. People are very bad at it. Give them a list of letters, and one letter will be missing. They spend a lot of time thinking which letter is missing. Right? Like, we're very bad at this, and a lot of retrieval systems are very bad. Like, give me, set difference. And so Graph can actually do that. So I'm going back to like, this is what GraphRAG actually gives, right? It gives us exhaustive set of members in a reply data set. And you can traverse. So basically what you can do now, you get a node, you can go to town with this, you can traverse, and from this node you can look at the neighborhood, and you can explore the relationship, and depending on what you want to do with it, right? You can basically have a multi-hop reasoning, right? What actually, you can iterate, and you can actually present it to the user and say, look, anything interesting to you? Do you want to follow? Like, what other questions do you want to ask? Right? Like, you actually have now paths for exploratory data analysis. And again, this does not exclude vector RAG. So what we propose here is that, agentic architectures are what's emerging. Like, how do we do GenAI? We don't do one-shot QA. Like, we ask a question, we get back results, we iterate on the results, right? We have a conversation. So when you have the conversation with this kind of data, you can actually route it to different kind of retrieval systems. You can do a vector X search where it's appropriate. Vector X are very efficient, right? What they have going for them, they're very well optimized for vast quantities of documents. It's basically like a little in-house Google, right? Like it's a lot of work. How do you do vector search? So Neo4j is not that. We have canonical vector search representation for reasonably sized data, but if you really want to have a huge vector RAG, we're not going to do that at that scale, that optimized, and just like Pinecone will do. So we partner with these folks, right? We integrate with all of the vector RAG providers, open source and closed source. And the beautiful thing, like it's actually like it's a very natural partnership because vector RAG companies understand this is an agentic world. We need to go from one to the other, back to the first. So you can find that we have open source ecosystem of integrations. And I actually see it as an AI graph stack. I see it as a kind of, in effect, as an open source AI stack, where we have this bottom-up partnerships with LangChain, Llama Index, Pinecone, Zillis, Weave8, like all the vector RAGs. You can find these packages on GitHub. And some of them are actually initiated by the partners, right? So like the vendor package with LangChain is in production, it's very solid. And you can actually look at it. It's our Python GraphRAG implementation. So if you really want just to play with one thing, just find Neo4j Python GraphRAG package, which is the standard vendor package for LangChain, right? And we work closely with LangChain. We have very tight integration with Llama Index. So any kind of retrieval now can be done with Neo4j, right? And I think going forward, right, this is how it really is going to grow in my mind. Like the open source ecosystem going to find what are the necessary, just like LangChain itself, what are the useful, really working best practices. Like nobody knows where GenAI is going, right? Like if somebody tells you, don't believe it, right? The best we can do is run fast and build. And so this is actually one of the best platforms to build on. You can have a knowledge graph, integrate with open source RAG like Zillis or others, and you can build the systems using the best practices, given examples you should have, and LangChain, Llama Index. So on November 14, if you're in the area, come to Amazon GenAI Loft. We're doing a massive meetup about this open source AI stack with LangChain, DivBot, and Neo4j. So we're going to have like this very deep dive. So DivBot built the biggest knowledge graph in the world. They're going to unveil, and we'll see how this works. I'm very curious. I've not seen this talk. So now some resources. So we have something called Graph Academy, which is one of the oldest and best maintained free resources. So this is an academy that everything I mentioned has a course about it, right? So there is a course on fundamentals of graphs, fundamentals of building the knowledge graphs and using them in LLM. And we're constantly adding courses. There is a deep learning.ai course on knowledge graphs and LLMs. And so this URL, this QR code link leads to this URL. Yes, and it's totally free. So that's my last slide. I'll leave it here for questions. And you can see the link. So the top link is the GitHub repository for the SSC Edgar notebooks I just described. The slides are at this short URL. The videos of talks about knowledge graphs and LLMs are YouTube channel called Functional TV. This is the Bay Area meetup. So this is a community meetup. There are Neo4j talks as well. So I'm linking to, if there is a version of this talk there, you can see. Okay, then just went out of presentation mode. Okay, so this is the Graph Academy. My email is here, and if you want to chat with me on X, LinkedIn, or Telegram, I'm chief scientist everywhere. And I've been an actual chief scientist at a public company, so I'm not making it up. And chief scientist of the talk is my medium. And finally, there is a resource I'm building with the community. It's called DevReal. So it's like DevRel, but for real, making AI real. Like, this is kind of how we envision doing open source AI. We'd like to collect best practices which developers are using. So if you're in DevRel in AI, there's a lot of problems. Like you have to go and teach developers when nobody knows actually how this is going to pan out. It's a very interesting time. So we're kind of collecting the best practices, how to ingest, absorb, understand AI as open source activity and share it with others. So I really kind of welcome everybody to join us, right? And reach out to me. This is a Ghost-based platform. You can sign up there, but I'd really like to talk to folks who want to contribute. And that's all I have. Questions?
I think we don't see the slide.
You don't see the slides. I'm so sorry. That's the AV. Somebody said AI is easy, AV is hard. Right? And yeah, this is actually done. It's interesting, like right at the end, it just sabotaged me. That's fine. Let me see if I can do it again. I'll bring it back. But while I'm doing this, we have some time for questions, right? Sure. So yeah, so you'll get the mic and feel free to ask your question. And put this on.
I'll do it.
All right, cool. I'll need to tickle it so it doesn't go.
Hi. So the advantage of graph search is apparent and great. But once you've looked up the information, is there anything special about how you pass it to the model?
Yeah, so there are several different interesting things you can do, right? You can actually construct, so like you deal with the candidate replies different, right? You get better replies from the model, right? You can select, so you can post-process them. But you can also ask the model to do different things. One of the best examples, you can ask it to construct the cipher, right? So we have a text-to-cipher retriever, which, so if the model basically can see that the question is about some set or subset of the graph, you can ask it to construct you the cipher, the query language, which will go to the knowledge graph. And if you have a massive knowledge graph, this is what you should be doing, right? You have this information. So we have an example where text-to-cipher actually is the best retriever, and we have that package being built. So we'll have it in production for customers, and this is an open source package, right? So that's, I think this is very different because others don't have this ability. I mean, it's similar to SQL database, right? Like you can have text to SQL, right? So you can do that. In the back.
Hey, thanks for a really good talk. Early on, you mentioned there's a distinction between subsets of graphs and layers of graphs.
Mm-hmm.
I'm not sure I understood. Can you expand on that, please?
Right. I mean, subset of graphs usually is subgraphs, right? So you'll have you can partition your graphs, and layers can basically they can span the whole graph and represent if there are people, like are these people for instance, if it's a science graph of scientists, are these people connected to Python OSS ecosystem, right? You can consider like the layer, like you can have graph subset by continent, for instance. Like there's a scientist in Europe, or you can subgraph. So in a way, it's a matter of speaking, right? Like you can basically subdivide the graph into physical components, and the layer will be logical way to connect different nodes in the graph.
From a practical perspective, what's the easiest way to get all your documents into a graph? Is there a model you pass it through and voila, you've got it, or is it something more complicated?
Yeah, so the LLM graph builder is an example of this, right? So currently, it's not an easy task, right? Like it's not solved. So I mean, like the steps you've seen in the manual creation of the graph. So the SEC Edgar notebooks demo, what it contains is a bunch of scripts which do the chunking, right? Which do the summarizing. So in a way, if your document set looks like that, you can do the same, right? Like normally you can chunk and summarize and hang all this. Like it just gives you an enormous amount already versus vector, because now you have everything linked with the summary. But you can think of other things. For instance, if you have this highly structured like financial data, you can actually require that everything has numbers, that everything has IDs, right? Like if you have some keywords, if you have things which are important to you, right? Like asset numbers, SKUs, you can actually require that at this point, these things are retrieved from a database and established as nodes, right? So it's kind of a mix of your internal knowledge of your internal data. And so normally you would go with a bunch of scripts, but of course we hope this can be automated. The LLM graph builder is an example, kind of naive kind of implementation, general purpose implementation. Take a PDF, like drop it. So entity extraction is a very typical step, right? Like probably it has names, let's extract all the names, people names, let's extract company names. Maybe we can use a library which understands these things, right? And establish them as nodes. So there are some things you can do for all documents, and some things will be proprietary to you.
If you know if you know your data very well, can you? Is there a way to channel it so you say, I want this to be the nodes and this to be?
Yeah.
Or is there a way to? How much can you control that?
We don't have a demo like this, but I'm super excited. There is a new startup called .txt, recently funded. We're gonna probably have like a joint talk. So what they do, they do structured generation, right? So when there are examples of this. You can tell give me JSON. Here's a schema for JSON, right? Give me an answer, and all these documents conform to a schema. So effectively, you can do this already, and .txt, they have this project called Outlines that do this even better, right? So you constrain it to give you a JSON schema, assuming that it will be filled, right? Like you need to validate it. And there was a problem, I think, with existing LMs that if you constrain it, the quality drops. And there was some paper saying like, here's how we can achieve structured output without loss of quality, right? So this is frontier research. But I think effectively what will happen, you will make it generate the JSON you can then drop into the graph, because JSON will be a collection of nodes, right? Like basically you will run over JSON populating the graph, and you will probably be validating JSON when you get it. And so the question is really how can you train them to give you JSON based on your data and make sure it's correct and without loss of quality.
Thank you.
Okay, well, apparently that's the time, so you've seen my handles. Super happy to talk, and especially if you're in DevRel, if you know how to teach developers AI, talk to me. I'd really like to learn and share. Thank you very much.